now we are entering to the quantum era. And the first speaker is Bence Bako from Wigner. And the talk is Fermionic Born Machines, Classical Training of Quantum Generative Models Based on Fermion Sampling. So Bence, the stage is yours.
Yeah, thank you very much for the introduction. Yes, my name is Bence Bako, and I'm from Wigner Research Center and Eötvös University. And this is a joint work with Zoltán Kolarowski and Zoltán Cimborás. And in fact, we will give two talks back to back. This first one is in a sort of fermionic setting, and the next one by Zoli will be one which is based on Gaussian boson sampling and bosonic models in general. And yes, I will introduce a generative model that is based on the fermion sampling quantum advantage scheme, and give you some context in this framework. But first, just to set the stage, I want to motivate why we care about quantum generative modeling. And of course, one big motivation is the fact that even the first or even the very recent quantum supremacy experiments were based on this promise that quantum computers can be used to generate samples from classically hard probability distribution. And what we want to do is make these probability distributions useful in some sense, and then use this ability of quantum computers to generate samples in an efficient way. And as a second part of the motivation, we also have this nice complexity theoretic results that basically show that even for some very restricted quantum circuits, classical sampling is still hard, in the sense that we can connect it to the collapse of the polynomial hierarchy to some level, but also some other hardness proofs exist for these very restricted circuit classes. And again, just to show you what I really mean by generative modeling, I mean that I'm given samples from an unknown probability distribution, and from those samples, I want to train a model that can produce new samples that resemble the original ones in some sense. So I want to learn some representation of a probability distribution Q that is close to the unknown distribution in some distance that I will define as a loss function, for instance. And of course, if I'm using quantum computers to build these model distributions, I have the promise that I'm operating in a large Hilbert space, so I have high expressivity. But actually training these models can be very challenging. And this is connected to barren plateaus, so the vanishing loss gradients and poor local minima. But most importantly, evaluating gradients on a quantum computer is much harder than in the classical case. So we don't have like backpropagation for quantum computers in general. And some kind of a solution could be to design problem-specific models that can be trained more efficiently by incorporating some symmetries or some problem structure, or considering restricted circuit classes that don't operate in that exponentially large Hilbert space anymore, but still retain some performance gain. And now the problem with this approach is that if I have provably good trainability, so provable non-existence of barren plateaus in these quantum circuits, then in many cases, I have a model which is effectively classical in the sense that I can estimate expectation values of local observables efficiently classically. And while this is a problem for a classifier where your final output is an expectation value, this can be something that we can use for generative learning, because for some circuits, I can estimate the expectation values efficiently classically, but I do need a quantum computer for efficient sampling in the final stage, so in the inference stage. And this whole framework is based on the reformulation of this loss function called the maximum mean discrepancy, using expectation values and then computing the difference or the square difference between expectation values of the target distribution and the model distribution, and then taking some convex combination of these differences. And this is a characteristic distance. So if I have a probability distribution that produces 0 maximum mean discrepancy for some kernels, then I know that I actually reproduce the target distribution. And this whole framework was introduced for IQP circuits, where it was shown that you can construct an unbiased estimator of the Z string expectation values, so Pauli Z operator strings, by just computing such cosine function and taking their average. Yes, for certain bit strings that you sample uniformly at random, and then you still get an unbiased estimator. But now again, this is for IQP circuits. But what we consider is the fermion sampling quantum advantage scheme, where the whole setup is very different. We have a quantum circuit that implements a fermionic Gaussian transformation, so an orthogonal, special orthogonal transformation on some input states. And if the input states are also Gaussian, then the whole thing is classical, even sampling everything. But if we input so-called magic states, which are not Gaussian anymore, then we have some nice promise of sampling advantage, so classical sampling hardness. And now the question is, can we actually estimate the expectation values for these circuits? So once again, we generalize this framework a little bit, where we also parameterize those magic input states. We have the FLO transformation, so the free fermionic or Gaussian transformation, and then we measure the first 3 qubits in each register of 4. And this way, we can, in theory, get any bit string on these marginals, basically. And now, just to give you a glimpse into how we actually estimate these expectation values, on each register of 4 qubits, we decompose the input state into 4 Gaussian, the sum of 4 Gaussian operators. And where these operators take this form is not very important for now. But still, if we then take the tensor product of these, we still get something that is exponential in the system size. So we cannot just propagate these Gaussian operators through the circuit. But we can do something smarter, which is what we did, is that for each of these decompositions, we take a state that would be Gaussian and then some correction terms. And these correction terms take this form. But the important part is that using this decomposition instead, we can estimate the expectation values of different length Z strings with different complexity. So if I only have one long Z string, then I can do with only the Gaussian part of each input state. Then if I have something that is 2 or 3 long, then I need to take into account the cases where I have a correction term in one of those registers. Then for 4 or 5 long, I need to take into account the case when I have 1 correction and the case when I have 2 corrections in 2 of the input registers. And with this, I get a complexity which is polynomial in the system size, and that polynomial is much better than if I just did Heisenberg time evolution backwards in the circuit. So this is one of the contributions that we have. And what is very different from the IQP case is that instead of having an unbiased estimator, these are all estimated exactly, well, up to numerical precision. And now if I have trained my circuit with these expectation values, then I can deploy it on a quantum computer. So I fix the input states, I fix the free fermionic transformation, and I only need to sample. And what is important is that these free fermionic transformations have a quadratic number of gates, so a linear depth, which is what we want. And now we tested this framework through some numerical experiments. where in the small cases, we could evaluate the final model, but in the larger instances, we could only do the training part because we don't have 160-qubit quantum computers hanging around in the GPU lab yet. So in this very first case, we considered these sort of Markov network structured problems over 12 binary random variables. And what we wanted to see is that if I just cut off the MMD loss approximation at different observable localities, do I get better and better results? And until which point is it worth actually estimating these? And what we saw is that in this very structured problem, since we know that it is actually, or it can be mapped to observables with locality up to 4, it is actually worth cutting off the MMD calculation at locality 4, where at locality 2 we would get back something called a Chow-Liu tree approximation of the probability distribution, and as we go higher, we get better and better results up to locality 4. Then we also looked at other aspects of this model. So for instance, we looked at that what is the effect of having multiple layers of those FLO transformations back to back, which is of course over-parameterizing that quadratic size subspace. But still we found that this is good for training. So we get better results, better information propagation through those circuits by over-parameterizing this subspace. And still in the inference stage, I can compile it down to just a single layer of these free fermionic gates. Then we went higher up. So we first considered molecular structure generation, where we took some small molecules from the Zinc-20 database, converted them to 60-bit long so-called Morgan fingerprints, so bit strings of length 60, and then we mapped it to a Fermionic Born machine with 80 qubits, and trained these models, and we saw pretty good results. But also we compared it with the model that doesn't have any magic input states. It only operates in the Gaussian setting, so it's fully classical. And we found that this magic is not only needed for sampling hardness, but it also improves the model quite significantly. And finally, just to show you the highest that we could go for now is for a problem which translates to 120 long bit strings, which we map to 160 qubits. So we could actually train models effectively for 160 qubits, and we still found some very good results, I would say, where on the left you can see the MMD loss computed at the end for different bandwidths, which is a parameter of the kernel that we use. And we compute that for a test set, which was not seen during the training, and still we found some good generalization results, basically. And now, just to summarize this framework that we introduced. So as I said, we have some fermionic magic input states. We have a Gaussian transformation, and then we can still compute expectation values of Pauli Z strings efficiently classically. From those, we can estimate this loss function called the squared maximum mean discrepancy. And with this, we can update the parameters in an automatic differentiation framework totally classically on a classical computer. And finally, we deploy the whole thing to a quantum computer. And in the paper, we also have some results that show that these circuits actually doesn't have or don't really have any barren plateaus. So we have good trainability properties, and we retain this duality of efficient expectation value estimation and classical sampling hardness. And now just only a final word as an epilogue, how this whole thing fits into a larger picture. This is all connected to the fact that spectral methods are quite natural for quantum computers, and some argue that they are also very much needed for machine learning purposes. because what happens in this MMD type of training, what we actually look at is the Fourier spectrum of the probability distribution, and we try to fit the Fourier spectrum of that probability distribution, which, for instance, in this case of binary random variables, so learning bit strings, is nothing more than the Walsh-Hadamard transform or the Fourier transform over this group, the product of Z2 groups. And if we want to generalize it to higher order random variables, or even to maybe continuous space, we would of course get some different Fourier transform. So thank you for your attention.
Thank you very much, Bence. Time for questions. Yeah.
Did you carry out these calculations in an emulator where you got the wave function, the amplitudes of the amplitudes, or did you think about carrying out this on a real quantum computer where you just get shots? And do you have an estimate how many shots would be needed to get to the precision which doesn't compromise your algorithm? So do you have an estimate for the number of shots?
Yes, so for the training, the goal would be to not use a quantum computer at all. So then we don't have any kind of shot noise. And this is not trained by a out-of-the-box emulator, so to say, but we actually built it from scratch, which is only specialized for this case and for only expectation values. So I don't actually have the amplitudes of the wave function, but I can only access the expectation values that I need for the training.
Yes, but if you get an outcome with a probability, you can very easily estimate from the binomial distribution what will be the sampling error. It will be the variance divided by the number of square root of number of shots. And do you know for what precision those probabilities you need in real life? So out of this, you can estimate without doing it how many shots you need. Do you have an estimate for that?
So you're asking that in the final stage when I train my model and I want to evaluate to see whether I am actually close to that distribution by sampling from a quantum computer, then I guess that to even evaluate something like total variation distance is not feasible. So in each case, you would get some exponential sample complexity if you would want to estimate these probabilities to high enough precision. You can do like cross entropy benchmarking maybe that people do sometimes to get some idea whether you're really close. But if my goal is to generate cat pictures, I can look at the output and see that, yeah, this is a cat picture. And I think this is what happens in real life, that you don't actually want to measure if I'm really close to that distribution, but whether I get samples that pass some sample test.
Okay. Any further point, please?
Yes, thank you so much. I have two questions. One is just related to training, and I'm curious if you can comment what kind of resources and how long training took in general.
Yes, so for now, we couldn't really find an efficient way to put this on a GPU. So these were all trained using CPU cores. They did consume quite a bit of memory, I think. But yeah, only those many cores that you can get in a CPU. So yeah.
Sure. The other question I have is related to this quantity that you were computing for the cost function. And if I understood correctly, you are using the target expectation value. But if I also understood correctly, you don't have access to the probability distribution.
Yes.
How can you get the target expectation value then?
Yes, so those target expectation values are mean parities of subsets of bits, and I have samples from the target probability distribution. So of course I cannot estimate them exactly, but if I have low order target values or low body terms, let's say 5, and I have 10,000 samples in my training set, then I can estimate those mean parities to pretty high precision.
Thank you.
Okay, thank you very much, Bence, again.